Okay, this is where we left off in the last video. We have set up the expression for the ratio of the volume of the sphere to the volume of the cylinder and expressed that in terms of an angle theta, so that we now have an expression or a function in terms of one variable that we can try to optimize. And what we want to do with this is, you should notice that as the volume of the cylinder reaches its maximum point, then the ratio of the volume of the sphere to the cylinder should reach a minimum point. And that's what we're going to do. So we're going to try to find the first derivative of this ratio, set it equal to 0, and then see where that occurs. And so we're looking for the derivative with respect to theta of the volume of the sphere to the volume of the cylinder. And that is the derivative with respect to theta of 2/3 secant squared theta times cosecant theta. We're going to use a product rule here and a chain rule within the product rule. So this would be our first function, and this our second function in the product rule. So we're looking for 1 d2 plus 2 d1. So that would be 1 d2. We're going to add to that 2 d1 now. And so we have cosecant theta. Now we need the derivative of 2/3 secant squared theta. And we start out by multiplying by 2, bringing down the 2. 2 times 2/3 secant theta, reducing the exponent from 2 to 1, leaving the inside alone. Now we're going to multiply that times the derivative of secant theta, which is secant theta tan theta. And that's the derivative of the second function. So what we want to do now is to just clean that up a little bit and try to find out where that's equal to 0. You should note that the first term is negative and the second term is positive, so we're going to write it as the second term minus the first term. And in the second term, there are some things that can be tidied up a bit. First of all, cosecant theta and tangent of theta. And these equal secant theta. And so what that really gives us there is secant cubed theta in the second term. It's 4/3 secant cubed theta. And minus 2/3 secant squared theta times cosecant theta cotan theta. Alright, so that's the first state, or the first stage of the tidying up here. From here I can factor out a secant squared theta, 2/3 secant squared theta. And that factor will never be 0. Okay, so we end up with 2/3 secant squared theta times the quantity 2 secant theta minus cosecant theta cotangent theta. And that will equal 0 when 2 secant theta is equal to cosecant theta cotangent theta. Now in red over to the left, if I multiply both sides by cosine of theta, I'm going to get cosine theta over sine theta quantity squared, which is just cotangent squared of theta. And so I'm looking for where the cotangent of theta is equal to the square root of 2. So on the right side I draw a little diagram, and since the tangent is opposite over adjacent, cotangent is adjacent over opposite, and that has to be square root of 2. And that makes the hypotenuse to be the square root of 3. So this is the value of theta. These are the ratios of the sides when theta is such that the volume of the sphere is at a maximum. And the ratio of the volume of the sphere to the volume of the cylinder is at a minimum. And I hope I said that the volume of the cylinder is at a maximum. So at this point we go back to our original expression, 2/3 secant squared theta cosecant theta, and the secant is root 3 over root 2, quantity squared, and the cosecant is root 3 over 1. We see that that gives us root 3 over root 1, and the final ratio is root 3 to 1. Cool problem.